Okay, I wanted to discuss how you would differentiate something through a method called differentiation by first principles. And essentially, you would have learned that if you had a graph. So let's consider your axis. I'm just going to consider the first quadrant of it. Let's say you just had a typical curve, one of the most basic ones. You had to have to excuse my drawing skills, but let's just say that this is x and this is f of x, and let's just say that this function is f of x equals x squared. Obviously, it wouldn't be this straight, but I think you get the idea. So, if you wanted to find the instantaneous slope of this function, you'd approach it by multiple methods. So you could start by drawing what's called a secant line. So essentially, let's say you wanted to find the slope of this point here, right? You could draw a secant line which is a straight line that touches the curve at 2 points. So in this case, it would be here and here. And that's not really accurate, right? Because you obviously have a large distance here, and the curve is, changing, or the slope is changing. So kind of what you want to do is reduce the 2 points into an infinitesimally close point. So essentially, your secant line would become smaller and smaller and smaller until you'd have a tangent line, something like this. As you can see, the line only touches the curve at 1 point, and then you find the rise over run, right? And then that would be your instantaneous slope for that point. But the problem with that is it's quite time consuming because you got to do it every single time, and in a test situation or any situation, it's quite time consuming. So we kind of need to mathematically formalize this instantaneous slope. And the way we're going to do it is, okay, so we'll consider the same graph, f of x equals x squared. And I'm not going to use actual numbers, I'm just going to use variables. So here, let's consider this to be x. So that's kind of where you start at, that's your position. Let's say you move some distance h, so plus h, then the final point that you would arrive at would be x plus h, right? It would be your displacement plus where you originally started from. So yeah, and then if we take this and we translate it onto the f of x or y plane, then you'd have x squared, right? Because you're just applying the function and you square it. And then in this case you have x plus h, so then the distance on the y or f of x plane would be x plus h squared. And just keep in mind that x squared plus h squared is not equivalent to this. You can't just distribute the exponent in. You gotta expand it through like binomial expansion. So the way we set it up like this is because this is rise over run. In algebra, you'd have learned that the slope is equivalent to the change in y over change in x. So that's pretty much what this is, right? Like you have your distance and distances, your differences of x's and your differences of y's and differences of x's, right? So the problem with this is that when you're considering a curve, this would only give you an average one. So let's kind of write this out. So if you say m is equivalent to so if you consider the y-axis or the f of x axis, then you'd have x plus h squared minus x squared, and then that would be all over your change in x. So you'd have x plus h, and you need to take away from your original position, minus x. So you'd notice that these two cancel out, and you're just left with m is equivalent to x plus h squared minus your original function all over h. So yeah, this is quite good. I mean, the problem we have with this now is that it's an average slope, so it isn't at one point. This kind of assumes a slope from this point all the way down here, and then on the y-axis it assumes it from here all the way down to here. So then you kind of need to narrow down to the point, like we were saying with the tangential line. So the way you would do that is through a limit, right? Because a limit essentially says that you gotta zoom in into one point. So kind of what you want to say is m is equivalent to the limit as, and now you gotta think about what variable would need to approach 0 for this to work. And remember that we said that we need the h to decrease to 0. We need it to approach 0 because you would need the 2 points to be infinitesimally close. So you would say limit as h approaches 0 of the same function. So x plus h squared all over h, and that is kind of messy, so just kind of make it a little bit clearer. Okay. So with that, we kind of have an idea of how to find the curve, but the problem with the slope of a curve. But the problem with this is that it's too specific, right? Because obviously you're not just going to want to find the slope of a quadratic. You'd also want to find it of any function, and you'll find that when we go to differentiating rules for finding derivatives, a lot of them are derived from this exact formula. So, I'm going to replace the m with this notation that you'll see throughout calculus. It's just dy dx. It's essentially saying that you're taking if you have just a straight line, you're considering a really small change in dx, a really small change in x, and then the small output that it creates, dy. So it is slope, but it's kind of expressing this instantaneous slope that we were discussing. So the way we kind of write this in function notation is dy dx is equivalent to the limit as h approaches 0, like we said, of, now we just get rid of the square and we can write it as a function of x plus h minus the original function, right? Because that's kind of where you're starting out at. And then that is all over your change in x or h. So then your function could be anything. It could be sine, cosine, an exponential, any other polynomial. So yeah, this kind of has that broad aspect of it. But something that you'll find is that if you just evaluate this for h equals 0, you would get a function that's undefined because you can't divide by 0. So kind of what you need to do is you need to manipulate it algebraically to get rid of that denominator, and then be able to apply the h approaching to 0. So let's consider the curve that we were looking at, which was f of x equals x squared. So f of x equals x squared. Now the derivative notation for this is f prime of x. It's like a dash, and then you would say, it would be whatever the derivative of x squared is, and then you just put that in there. So let's use the limit definition to find it. So if you have your dy dx, and that is equivalent to the limit as h approaches 0. And let's see, we already said that this was the formula for that, right? You kind of just, when we saw it on the graph, you kind of just square the x plus h, take away the original function, and divide it by the change in x. So you'd have x plus h squared minus x squared all over h. So that is equivalent to limit as h approaches 0. And now what you kind of want to do is expand this. So if you have x plus h squared, this is equivalent to x plus h times x plus h. And if you would expand this out, you're doing distributive property twice, right, to all the variables. Well, that's kind of a mess, but you get the idea. This would turn out to be x squared, right, because you multiply this x by this x. And then you'd have x plus h. And then when you're moving on to the h, you'd have h times x, so plus xh again. And then you'd have plus h squared, right? So it's not just x squared plus h squared. So if you simplify this down, it becomes x squared plus, well, you have two of these xh's, so it becomes 2xh plus h squared. So what that means now is you can, substitute that all back into the equation. So you'd have x squared plus 2xh plus h squared minus x squared all over h. And like I was saying, you can kind of just simplify this denominator down and get rid of it. So limit as h approaches 0. And look, if you can notice here that this and this cancel out, so that makes 0. This and this cancel out, that makes 0. And then this exponent decreases by 1, right? Because h squared divided by h is just h. So here you'd have 2x plus this h value. And now we can evaluate the limit since it's out of the denominator. So you'd make this equivalent to 0, and then you'd get, well, no, you wouldn't have the limit anymore. You would just have 2x. And this makes sense, right? Because obviously you wouldn't have just a number, because that's only for linear equations. You need to plug in your value of x, and then that will tell you the slope of the function. So if you wanted to find the dy dx at, I don't know, x equals 3, then dy dx would just be equivalent to 2 times 3, which is 6. So you kind of just double the x value for every increment. And yeah, that's kind of the basic idea of it. So this is a building block of derivatives, right? Every differentiation rule that you learned, the chain rule, the power rule, finding the derivatives of exponents, the trig rules, all of that will stem from this basic idea of a limit. And yeah, I hope that helped you, and yeah, bye.